We will now take a look at chapter 10, which is all about exponential and logarithmic functions. Before we start applying calculus tools to them, though, let's do a quick review of what those functions really are. So this video is the pre-calculus, sort of just-in-time support for exponential and logarithmic functions. If you need more practice with them, please take a look at pre-calculus review package, where you'll find more examples and exercises and explanations about what exponential and logarithmic functions are. So exponential functions are of the form y equals a to power x, where a is some positive number, okay? So for example, for our first graph here, let's take a look at the functions 2 to power x and 2 to power minus x. Recalling exponential laws, which I hope that you can, again, either remember or look up so you're more familiar with them. Remember that negative powers are actually positive powers, but on the bottom. So 2 to power minus x is actually 1 over 2 to power x, which alternatively can also be written as 1/2 to power x. Now, if we would like to sketch these, and if you don't remember the shape, the first thing to do is to construct a table of values. So I'm going to construct both of these graphs within the same table of values. So I'm going to have x, 2 to power x, and then 2 to power minus x. Now, whenever you construct a table of values, the one thing to remember is that you do want to pick a variety of numbers, so don't discriminate against negative numbers. You also want to know what the graph looks like on the negative side. So let's plug in, say, 0, 1, 2, -1, -2, and then hopefully that should be enough for us to see the shape, and if it's not, we'll plug in more numbers. So 0, if I plug in 0 up into the power, 2 to power 0 is just 1. 2 to power 1 is 2. 2 to power 2 is 4. 2 to power -1 is 1 over 2 to power 1, so 1/2. 2 to power minus 2 is 1/4. Okay, and then when I'm plugging in for the 2 to the -1, feel free to pause the video here and actually try the numbers for yourself. You will notice that if I plug in 0, I will also get a 1. In fact, anything to power 0 is 1. 2 to power -1 is 1/2. To power -2 is 1/4. But then here, something interesting happens. If I plug in -1 into the minus x here, I'm going to get 2 to power -1. So 2 to power 1, or just 2. And similarly for the next one is 4. So we see that these graphs actually flip the values around. Let's now try to actually sketch them. So we're going to go through the points for the first graph of 2 to the x and sketch those on the graph. So at 0 I have 1, at 1 I have 2, at 2 I have 4. And on the negative side, I get -1/2 and then -1/4. And I know that this trend will continue. The higher the power, the higher the graph will grow. The smaller the power into the negative, the smaller of a fraction I'm going to get. But it is important to notice that I'm never going to be able to get a negative number, right? No matter how big a negative number I plug in here, it's going to get smaller and smaller in fraction, but never turn negative. So this is 2 to power x. If I'm sketching 2 to power -x, I will note that it's the exact same graph, but flipped in the y-axis. So it's going to be the graph that is actually decreasing this whole time. Now, one thing to note here is anything to power 0 is going to be 1, which means that no matter what exponential function I have, I will have the y-intercept at 1. Great news. We now know what an exponential graph looks like for positive and negative powers. This is just for one value of the base number, though, which is what a is called. Let's take a look at how that compares between different bases. So here I have 3 to power x, 5 to power x, 4 to power minus x, and -4 to power x. Notice with this last number that it's actually 4 to power x, then all negated. So it's not -4 to power x, because for the definition of the exponential function, the base has to be positive. So this is actually just a negation of an exponential function. Take a minute here and actually sketch these graphs using the table of values to see how they work on the same graph together. How does the base affect the shape of the graph? This is what you should get. So you notice that the graph with 3 to the x will rise slower than the graph of 5 to the x. So for example, if I now try to sketch 4 to the x, it will be somewhere in between them. The negative powers will be the graphs that are the same but in the decreasing manner. And if the whole function is negated, then it's going to be flipped around the x-axis. A couple of general trends are becoming pretty obvious about the exponential functions. Specifically, if I take a limit of an exponential function as x goes to infinity, a number raised to a really large power is a really large number, so this will be infinity, which means that generally the exponential functions grow when a is bigger than 1. If I have a fraction, that means that I really have a negative power like I did here, which means that the shape of the graph will be decreasing. So the limit as x goes to infinity of a of x is equal to 0, approaching the x-axis for the values of a less than 1. Remember that for our exponential functions, a have to be positive. So in both of these cases, a's are actually bigger than 0. The other thing to mention about exponential functions in general is that the reason these are so useful is because they model processes that multiply or divide by the same amount within the same time frame. So for example, this graph of 3 to the x will model something that gets tripled every fixed time interval. Let's say every week, if my x-axis is in weeks, the number of, let's say, bacteria gets tripled. The functions that are exponential but decreasing will model processes such as decaying, which is the case with things like radioactive materials, where we hear words like half-life, which means that every fixed amount of time, the amount of material gets halved, divided by 2. They will also model things like how the drugs get absorbed and processed by the body. We will see a number of different applications of exponential functions throughout this entire chapter. Let's next take a look at something a little more calculus inspired, and that is let us attempt to find a tangent line to the actual exponential function at a particular point, at 0. It is going to be at the y-intercept, so we will be looking for tangent lines right at this point right here. Let's see if we can come up with a general equation to describe them. So, as always, we will start with y minus y naught equals mx minus x naught, where m is our slope. So the point here is x equals 0, which means that y equals 0 is a to power 0, which is, of course, equal to 1. And this m is the slope. Now, I don't yet know how to take the derivatives of exponential functions, so I will leave the slope value as just m. What do I have otherwise? I'm going to have y minus 1 is equal to mx minus 0, or if I expand it out, I'm going to have y equals mx plus 1. Well, this is a very nice equation where all I have no idea how to describe yet is the actual slope. What we can do is try to eyeball it from the graph and see if we can see something interesting. So let's take a quick look at what these functions look like. So here I have, let's say, y equals 2 to the x, and I have a line with equation y equals mx plus 1. M is supposed to be the slope of this function at 0. So I'm simply going to slide the slope around until I can be fairly certain that I have approximated the slope to be something. So I would say that this looks like a pretty good approximation of the tangent line at 1. And so my slope there is approximately 0.69. Okay, what if I wanted to take a look now at 3 to power x? Well, I know from what we've just sketched that that graph will rise quicker, which means, so let me take away the 2, which means that the tangent line for 2 to the x is no longer the tangent line to this graph. So if I try to eyeball what this tangent line look like here now, I would say it's something like this, right? This looks pretty tangent at 0. So the value here that I have is 1.13. Now, this is a complete approximation. I'm not after any kind of rigorous definition. But what is Interesting though is that for when I looked at the graph at 2 to the x, my slope was just below 1. When I looked at the graph of 3 to the x, my slope was just above 1. So now I wonder, what should the base be for the slope of my line to be exactly 1? So what is this line with the slope of 1 actually going to be tangent to? There must be an exponential curve that this is tangent to at 0. And that is indeed the case, and that curve is e to power x. So the base number for which the tangent line has slope 1, the perfect diagonal line here, is that constant e, the natural exponent. So I've just summarized all of our findings on this slide here. For 2 to power x, the slope was less than 1. For 3 to power x, the slope was bigger than 1, which means that for some number between 2 and 3, the slope is 1. And that number is what we call e. In fact, it's such a nice number, I'm going to put an exclamation mark here. That's what e is. E is a number for which the slope of the tangent line at 0 is equal to 1. Now, e itself, if you plug it into the calculator, you'll notice that it can be approximated. It's never ending, it's transcendental, which means that there is no end to its decimal expansion, but you can approximate it with something. It's approximately 2.7. A lot of problems, particularly in this course, because of their applications to biology and other life sciences, will use e as a base, as opposed to some actual number, like to some whole number, like 2 or 3. This base will become extremely useful in most of the things that we're going to see. And in fact, we will generally use both exponentials and their inverse functions with this base. Now, speaking of inverse functions, let's take a look at what that actually means. Once again, this is going to be a quick introduction to what inverse functions actually are. For a more detailed explanation of what they are as an abstract concept, please take a look at the precalculus review package. But the idea behind exponential functions is this. Let's say I have x, my input. If I apply function f to it, I get some output f of x. If I would like to reverse the process and go back, I'm going to apply what we call an inverse function, and we have the notation for it, f of f to the power minus 1. Now, the notation is not the best, so please be careful. F to power minus 1 of x is the notation for the inverse of the function f, not the reciprocal. So this is not the actual power. So this is not 1 over f of x, okay? The notation is not the best, but it is a good shorthand. We will talk about inverse a lot more than we will talk about the reciprocal, so it makes sense to use that as a shorthand, okay? In the most reasonable way, the word inverse is exactly what it means in English as well. So for example, for just a really quick intuitive example, if my function is, let's say, 5x, so my function multiplies everything by 5, then its inverse is going to do the exact opposite or revert the process, which means to divide by 5. So in this case, the inverse function will just be x divided by 5, okay? If my function was to add a 3, then the inverse would be to subtract a 3. So verbally, the inverse function simply undoes what the original one did. Symbolically, we write that as if I apply my function to x first, and then I apply the inverse, then I'm simply going to get my x back. Whatever f did, f inverse undid, and I was able to get my original value of x back. Now, it doesn't matter what order you actually apply inverses, the functions in. So if I apply the inverse first and then the function, I should also get my x back. Both are functions, both can be applied in any order. Analytically, we say that we actually reverse the roles of x and y. And if you were to solve for it, or if you remember from precalculus how you would solve for it, this is how you would find an inverse. You reverse the roles of x and y in your formula, and then you solve for y to get, once again, an explicit function of x. Graphically, reversing the roles of x and y means flipping the graph along the y equals x line. So we do this a lot. Again, in pre-calculus, you've probably seen that. And we will come back to this once we talk about the graphs of the inverses of the exponential functions. The one thing that does mean for the function, though, is that for a function, in order to have an inverse, it must also pass the horizontal line test, the test for actually having an inverse. Thinking about inverse functions in terms of exponential functions, the inverse of an exponential function is what we call a logarithmic function. So the exponential function itself, the way to calculate this, the process is fairly straightforward. 2 to the power x means that we raise 2 to the power x. The opposite process will ask, what power did we have to raise to get the outcome? So in the logarithmic function, we're after the power. So if you're trying to compute logarithm, first of all, you have to look at the base. Here it's 2, and then the inside. And in order to actually figure out what the number is, this will correspond to the power to which you had to raise this base 2 to get this number x. Now, just to get a little bit familiar with the calculations, let's do a couple of examples. So, for example, logarithm base 2 of 8 means I am trying to figure out what is the power to which I have to raise 2 to get 8. So 2 to what power is equal to 8? Well, these are nice numbers, and I can see that that number is going to be 3. So this logarithm value is 3. 3 is the power to which I have to raise 2 to get 8. Okay, let's take a look at the next one. To which power did I have to raise 3 to get a 1? So maybe on the side here, 3 to which power is equal to 1? Well, anything to power 0 is 1, so this logarithm is going to be 0. Next one, 3 to which power will result in 0? Well, we've discussed that on the very first slide in this video. Nothing, no power will give me 0 or a negative number. So this does not exist. A logarithm cannot have an inside of 0 or anything negative because no power will be able to give me a 0 or a negative number as the actual result. To what power did I have to raise 4 to get a 2? So 4 to which power is equal to 2? Well, I have to take a square root of 4 in order to get a 2, and a square root is a power of 1/2. And then finally here, to which power did I have to raise 4 to get a quarter? So let's write this down too. 4 to which power is equal to a quarter? Well, we notice that 4 just got flipped to be on the bottom, and that corresponds to negative power, but 4 stayed 4, so the power here is -1. Logarithms have an incredible history of how they were actually discovered and where the word comes from. When they were originally discovered, they were not discovered as inverses of exponential functions, but rather as a really useful tool in navigation and approximations of small numbers. We will talk about how that's useful in log-log plots and semi-log plots and seeing the difference in trends. For example, I am sure you guys have been seeing log plots in the news about the pandemic, and that is the main application of logs for when they were first discovered. However, they also luckily turned out to be inverses of exponential functions, which allowed us to do much more efficient computations with them. The next slide is completely for you to actually practice with, but I will go through one line just to show you what the slide here is after. It is just getting a little bit more familiar, switching between an exponential form, a logarithmic form, and what they mean altogether, so that we are better prepared to solve equations that involve exponents and logarithms. So the first line here is completely filled out for you. 2 to the power 3 is 8. which means that logarithm base 2 of 8 is equal to 3. Sometimes it's easier to go the other way around because this is the power to which you have to raise 2 to get 8. The other way to think about this is logarithm 2 base 8 is the power to which you had to raise 2 to get 8. So instead of writing a 3, we can write log base 2 of 8 there. Sometimes logarithms are not going to be nice whole numbers, so this notation will come in handy as well. So with the same type of logic, please go through and actually figure out the other lines. Once again, just so you get familiar with the notation. And then the next slide is just talking about comparison. Of course, you'll have calculators that can calculate the exact values of the powers and of logarithms. But again, just to build intuition and how this will help us in solving the equations, it's a really useful exercise to get familiar with the notation. I'm not going to go through the power ones, but let me just talk maybe a little bit about this logarithmic one. So it's asking which one is bigger, log base 9 of 80 or log base 9 of 82. Remember that logarithm is the power to which you have to raise the base to get the result. So this first logarithm is the power to which you had to raise 9 to get 80. And the second logarithm is the power to which you had to raise 9 to get 82. Now the powers here might be easier to compare than the actual log values. So all of these exercises you can do without a calculator. And I strongly encourage you to, in fact, do just that, once again, so that you're more familiar with how the power functions work, the exponential functions work, and so that you're more familiar with the logarithmic notation so we can use it later more efficiently in applications.